Everyone. Myself Rishiraj, a third year EC undergraduate student who will be showing you an experiment on sampling, aliasing and reconstruction. So basically this topic is related to a subject which is in our domain called digital communication. The main objective of this experiment are to verify sampling theorem, observe the effect of aliasing and reconstruct a sampled signal using sciencey interpolation. And I have implemented this experiment using Python in Google Colab. If anyone wants to do this experiment same, so they can use MATLAB Simulink for their operations. Without further wasting any more time, let's get started. For this experiment, I have used a two-tone signal given by x of t is equal to sine of 2 pi f1 t plus 0.5 sine 2 pi f2 t. Now here, as you guys can see, I have taken f1 and f2 as 50 and 100 hertz. Now from these two, by the given condition, we can easily observe that the f max becomes 100 hertz. That is, the maximum frequency present in the signal is 100 hertz. According to the sampling theorem, the sampling frequency should be at least twice the maximum frequency. Therefore, the Nyquist rate for this signal is 2 times f of max, that is 2 times the maximum frequency which we obtained from here, that is 100 hertz, means 2 into 100, 200 hertz. Now as we are getting the Nyquist rate for the signal 200 hertz, so I have tested 3 different sampling frequencies: 250 hertz, 200 hertz and 150 hertz. Now you will easily get to know that why I have taken such random values like 250, 200 and 150, because there are some reasons which I will be explaining later on. Now the case 1 for 250 hertz. Now I will be scrolling down at the bottom so that I can show you the waveform which I obtained while taking the maximum frequency as 100 so that the Nyquist sampling rate becomes 200 hertz, and where we included 3 such values: 250 hertz, 200 hertz and 150 hertz. So without further wasting any more time, move on to our case 1, that is 250 hertz as our sampling frequency. First, I have taken the sampling frequency of 250 hertz. Since 250 hertz is greater than the Nyquist rate of 200 hertz, the sampling theorem is satisfied. In this graph, the smooth curve represents the original signal and the individual point represents the samples. Since the sampling frequency is sufficiently high, the sample contains enough information about the original signal. I then use sciencey interpolation to reconstruct these from samples. That means that from these samples, that means the orange colors, we have used this sciencey interpolation to reconstruct the sciencey reconstruction waveform. As we can see from the reconstructed waveform, it follows the original waveform quite closely. Therefore, for 250 Hz sampling, aliasing does not occur and the reconstruction is successful. See, the error is negligibly linear. That means the reconstruction error or the error for the case of 250 Hz is negligible. And here are the waveform for reference versus reconstructed spectrum for the case of 250 Hz. Now, case 2. In the second case, I have taken the sampling frequency as 200 Hz, which is exactly equal to twice the maximum signal frequency. Therefore, this is the Nyquist rate case. Ideally, according to the sampling theorem, reconstruction is possible at this rate. The reconstructed waveform follows the original signal, although some small reconstruction error can be observed in the simulation. This error can occur because the simulation uses a finite samples. Like as you guys can see, this uses finite samples and a finite time intervals. 0.00, 0.02, 0.04 like this finite intervals. Whereas ideal sciencey reconstruction assumes as infinite number of samples. Therefore, this case demonstrates the behavior of theoretical Nyquist limit. Here is the reference versus reconstructed spectrum plot for the case of 200 Hz. Now, the most important case, case 3, that is 150 Hz. Finally, I have taken the sampling frequency as 150 Hz because this is less than Nyquist rate of 200 Hz. Therefore, the sampling theorem is violated and here aliasing occurs. The original signal contains a 100 Hz component. The aliased frequency can be calculated manually using f of alias equals to absolute modulus of f of 2 minus f of s. So for this case, the second frequency which we have taken here was 100 Hz and the sampling frequency for this case is 150 Hz. So the 100 Hz component appears here as a 50 Hz component after sampling. Now this can be observed in the frequency domain spectrum where the frequency component folds into lower frequency regions. Because of this aliasing, the original signal cannot be perfectly recovered through reconstruction. As you guys can see that the original signal was something and the reconstructed or the recovered signal is something. That means we cannot recover what was the original form obtained in the previous. And here is the reference versus reconstructed spectrum which we obtained for the 150 Hz case. And I have also calculated the reconstructed error by subtracting the reconstructed signal from the original signal. Like for in this case, we obtained 50 Hz and from the other two cases, we have also obtained the reconstructed error graphs. The error is relatively small when the sampling theorem is satisfied, while the undersampled case shows a significant difference because of the alias. And here, the undersampled case refers to this 150 Hz case. And I have also used here the fast Fourier transform to obtain the magnitude spectrum and compare the original and reconstructed signals in the frequency domain. Now this allows us to clearly observe how the frequency components behave during sampling and reconstruction. Now as you guys can see that I have taken the frequency data as 50 and 100 Hz in the beginning here in the code. Now, if anyone wants to change the value and see that what are the waveforms which we are getting, what are the waveforms if we change the F1 and F2. So they can change by doing like simply here in F1, we can write as take example as 20 and take example as 80. So here easily we can see that the maximum frequency here will be 80 Hz such that our Nyquist rate becomes 160 Hz. Now as the Nyquist rate become 160 Hz, now this range will also get changed. Now this ranges becomes like 200, 160 and the undersampled case will be say 120 Hz. Sorry, 120 Hz. Now by doing this, we are running this and we will be observing some changes in the waveforms like then they will not be like the previous one which we obtained for 50 and 100 Hz. See the changes that you can observe here for 20 Hz or 80 Hz as our input frequencies such that the maximum frequency we take as 180 Hz and the Nyquist sampling rate becomes 160 Hz. And the three cases 200, 160 and 120. The 200 is the above Nyquist rate one and 160 is the equal to Nyquist rate condition and the 121 is the below Nyquist rate condition as you guys can see. And here also same where I have drawn the reconstructed error graphs for better visualization. Okay. To conclude this experiment, This experiment verifies the importance of sampling theorem. When sampling frequency is greater than or equal to the Nyquist rate, the signal can ideally be reconstructed from its samples. However, when the signal frequency falls below the Nyquist rate, aliasing occurs and the original frequency information is lost. In our undersampled case, the 100 Hz component was observed at the aliased frequency of 50 Hz. Therefore, this experiment demonstrates sampling, science reconstruction error, and aliasing, both in time domain and frequency domain. I hope you enjoyed it and liked it. Thank you.